So, after the short break, we're back to discuss the costs incurred by LNG as a ship fuel. So, with regard to the costs associated with converting the marine vessel to LNG operations, natural gas is not compatible with existing liquid fuel systems and requires modification of existing engines and changes or additions to the existing shipboard fuel systems, as well as other changes for safety reasons. The conversion to LNG as fuel required changes to the marine engine conversion of MCC to MEGI. The LNG insert gas needs also retrofitting the auxiliary systems, the LNG storage tanks, the fuel supply system, the removal of existing piping equipment, as well as tank foundations, deck houses, and foundations. The table above shows the costs associated with converting 3 vessels of different sizes to accommodate natural gas. As we can see, depending on the type of a vessel and the size, the engine cost varies significantly from 1.2 million for a tugboat to 4 million for a bulk carrier, while the fuel system cost is again high, ranging from $6 to $20 million, while the total cost of conversion may rise to 70.2 million to 24 million, depending on the type of vessel and the engine. The vessels, however, due to this cost, vessels are seldom retrofitted due to reasons that relate to mainly the vessel life. Most vessels are assumed to have a life of 30 years rather than 60 years that WSF projects. As a consequence of the shorter remaining life of a vessel, there is less time to amortize the investment. While an additional factor is the impact on capacity space or other economics. In some instances, vessel owners have decided against a retrofit because in Europe, the fuel tanks are in the vessel's hold. LNG requires more volume for the same energy output than diesel, and as a consequence, vessel owners face the possibility of losing capacity space because of additional space needed for the larger fuel storage tanks. A second incurred cost relates to the construction of LNG vessels and the payback time. With regard to that fact, the cost of building a new ship powered by natural gas has a premium over the construction cost of a conventional ship with fossil fuel. There is a cost increase for the gas engine and another for the gaseous fuel system associated with the LNG storage tanks. A Germaischer-Lloyd study in 2009 noted an additional investment approximately to 25% over that of the cost for constructing a typical new container ship, while another study from the Danish Maritime Authority details information on the return on investment or payback for LNG and HFO scrubber compared with the use of MGO as fuel for the ships operating entirely within ECAs. As we can see in this table, where the payback time relative to MGO complies a strategy for LNG and HFO with scrubber. In all case scenarios, as we can see, for different types of vessels, the payback time for the scenario 1 of HFO with a scrubber for RoRo is 2 to 3 years, for a tanker the same, while for the container is 1 to 2 years for retrofitting, while for an LNG respectively it's 1 to 2 years for RoRos, 2 to 3 years for tankers, 1 to 2 years for containers. While for new buildings, the payback time is again 1 to 2 years for RoRos, retrofitting, 1 to 2 years for RoRos, 2 to 3 years for tankers, 1 to 2 years for containers, and again 1 to 2 years for big RoRos. Respectively, the payback time for a new build LNG carrier is 1 to 2 years For ROROs, 2 to 3 years for tankers, 1 to 2 years for containers, while also for big ROROs 1 to 2 years. Further on, a study by Mann and GL on the use of LNG to fuel container vessels indicates a payback time less than 2 years for a shipping sailing in the ECAs, about 65% of the time, based on the current differences in fuel costs. These conclusions are roughly in line with the above-mentioned study. According to another DNV report, if a ship spends more than 30% of its operating time in an ECA, the cost of investing in gas fuel engines can be justified. As it can be seen in this graph, the payback LNG technology depends on the size of the decisively on the size of the vessel. As we can see, small container ships of 2,500 TEUs have a quicker payback time in relation to vessels of container vessels of 8,500 TEUs, or even large vessels of 18,000 TEUs, which have a considerable much more payback time in order to amortize the investments required. On the basis of daily cost figures for conventionally and LNG fuel ships of different types and sizes, Royal Haskoning has calculated the relative costs. The LNG fuel ships are estimated to have a 10% more capital cost than diesel fueled ships. They tend to have a capacity reduction from 2 to 5%. They tend to have also increased operational and insurance costs. However, they present fuel reductions of about 60 to 80% of heavy fuel costs on a net energy basis. The study concludes that LNG fuel ships are between 10 and 25% cheaper for respectively Panamax bulk ship operation outside a SECA while in a high relative fuel price scenario, and RoRo pack ship operation inside the SECA in a low relative fuel price scenario. Then we move forward to the costs associated with LNG tank selection and loss of capacity. LNG storage tanks require more space than traditional fuel oil tanks, which may reduce cargo capacity depending on type of vessel, the type of fuel tank, and the availability of a suitable location for the LNG tanks on board or in a tank room within the ship. The challenges that exist in the storage of natural gas are the low temperature, which also requires special construction materials such as stainless steel and aluminum, special insulation, and provision of contraction of the tank, while challenges also include with regard to the easy ignition and lower weight when it is warmer than the air required, adequate ventilation and other safety measures, large volume tanks, and finally the location of the tanks. The current regulatory approach is based on self-supporting tanks as defined by the IMO IGS code. Type A, designed as ship structures, and Type B, prismatic and spherical, tanks are generally feasible for fuel gas tanks, but the requirement for pressure, maintenance, and secondary barriers raise problems which have not yet been solved in a technically and commercially sound way. This may be a future solution for ships carrying large amounts of LNG as a fuel. Hence, IMO Type C tanks, pressure vessels, turn out to be the most preferred solution for current designs. Additionally, besides the fact that LNG tanks require extra volume due to the low density of LNG and the tank shapes and insulation, some tank volume is required to be reserved for LNG expansion and for residual LNG heal in the empty tank to keep it cold. The tank's relief valve pressure drives the limit placed on the loading level. The reason for this is that LNG density decreases quickly as heat is absorbed and its temperature and saturation pressure increase. The higher the temperature and the corresponding saturation pressure, the lower the density. Current IMO regulation limit LNG tanks to 98% full at the relief valve setting, where it is the maximum allowable volume. Loading a tank with LNG at minus 162 degrees when it's close to atmospheric pressure is a desirable loading condition because at that condition LNG can remain in the tank for the longest period of time before heat absorption raises the tank pressure to the relief valve setting. At this initial loading condition, the LNG density will be at the highest value. Since the mass of LNG remains the same as the pressure is building, and the LNG density is going down, raising the level in the LNG tank, the ratio of the densities between the LNG when bunkered and when at the 98% full limit determines the loading point, the level the tank can be loaded while bunkering. Finally, the higher the relief valve pressure, the lower the loading limit. But on the other hand, the higher the relief valve pressure, the longer the LNG can stay in the tank. Besides the limit of filling, usable tank capacity is further reduced by the common practice of leaving LNG in the bottom of the tank of about 5% to continue boiling off, keeping the tank cold until the next bunkering. Cooling down an empty, warm tank before it can be relieved with LNG takes a long time and is normally avoided. In this picture, we can see the types of LNG tanks along with their characteristics. We can distinguish from B and C types of LNG vessel tanks, where the heat installation in the first ones are external, while only for the C type of cylindrical tanks includes a vacuum, and a tank track also includes a vacuum. The costs associated are extremely high for B types, prismatic tanks and spherical tanks respectively, while when considering cylindrical tanks, the average cost is down to a medium cost of investment. Further on, another incurred cost and a barrier to the LNG adoption is the bunkering infrastructure. One of the significant barriers to adopt LNG as a fuel is the fact that there is no infrastructure established among the supply chain network in place that can enable LNG delivery. Since the demand for LNG supply is still not high in the commercial shipping industry, the gas providers and bunker suppliers do not want to invest in the necessary infrastructure until they see an increase in demand. At the same time, since the supply chain and infrastructure are still not developed to be able to deliver LNG, the ship owners are not willing to invest in LNG fuel ships. This is considered as one of the main obstacles preventing of the widespread adoption of LNG as fuel and reminds of the classic chicken and egg problem, or else who will move forward to make the investment first? Will it be the port developers, or who will initiate the investment processes to invest in bunkering infrastructure, or will it be the ship owners who will firstly build their LNG fuel vessels and afterwards the infrastructure to accommodate them will be required to be made? So, the costs with regard to the port infrastructure take into account the business model for LNG terminals in ports hinges on four major factors: regional maritime demand for LNG, available for liner shipping mostly, availability and type of neighboring terminals, demand by non-maritime stakeholders with regard to road, inland navigation, industry purposes, and power generation, while the last of these three criteria has a major influence on the availability of any large import terminal that combines the supply of LNG to ships with import activities. The larger the terminal, the lower the distribution costs. As we can see in the first picture, the cost of the distribution for a large cost of LNG distribution at a 10 years payback time for a large LNG terminal is $118 per ton. But as we move to the medium, the cost increased to $137 per ton, while for small LNG terminals, the cost rises to $194 per ton, meaning that the large LNG terminals might exploit significantly the economies of scale that will incur. However, in any case of building LNG port infrastructure, the financial costs from an investment and operational point of view are considerable in any case. The total investment cost for a large-scale LNG terminal is estimated to be around $69 million, while respectively in a medium case, the total investment rises to $137 million, and in the small cases, which is the most economical solution, but with deficiencies in the supply and the accommodation of vessels, is only $15 million. Finally, in order to solve the LNG infrastructure problem, it is necessary that the port authorities, ship owners, local communities and other stakeholders work together on assessing the current and future demand for LNG in ports to plan and establish a sufficient number of LNG infrastructure. Since many owners are willing to spend on LNG propulsion, the number of LNG infrastructure will increase, and as demand for LNG increases, the incremental cost of infrastructure will naturally decline. Many governments have announced their support for LNG as a fuel navigation. In Europe specifically, for example, the European Commission published in January 2013 a new directive aimed at assuring new infrastructure for alternative clean fuels. The project identifies LNG as the most convenient for shipping fuel. Therefore, the European ports is most likely that will be able to provide sufficient LNG cargo services. As we can see in this graph, we can see some ports and whether they have or not developed bunkering infrastructure. As we can see, in regions apart from Europe, only in India and in Singapore, we can find bunkering infrastructure for LNG, while in other places like New York, Shanghai, Vancouver, Houston, Fujairah, Piraeus, Algeciras, as well as Southampton, an LNG bunker infrastructure does not exist, and these ports aim to have established their own port infrastructures to accommodate LNG ships, most of them on 220 when the regulations are enforced, or even further. As we said, Europe is the only continent that has so far developed most of LNG bunkering infrastructure, including ports such as Gothenburg, Zeebrugge, Rotterdam, Antwerp, and Antwerp, which are some of the busiest ports in Europe, and in order to sustain their development and their market share, they have to be like the entrepreneurs and the ones that develop they are the first ones to develop LNG infrastructure to accommodate LNG fuel ships. Finally, we reach the end of our session, where a summary and some concluding remarks will be presented. So, summarizing the cost and benefits of LNG use as an alternative fuel. Among the benefits, you can consider that LNG offers considerably improved revenue, improved environmental footprint sufficient to comply with the annexes of the IMO regulation, energy efficiency increase by installing low improving appendages during dry docking, reduction of the main engine maintenance hours, less engine crew is required, cheaper lubricants also are required, while LNG results in cleaner engine rooms, no soot on decks and therefore less cleaning and wash water needed, no need for exhaust cleaning devices or catalytic reactors, while finally it ends up with a slightly lower noise level in the engine room. Respectively, on the costs and uncertainties occurred for the LNG fuel, for the LNG as an alternative ship fuel, we can distinguish the shipbuilding costs, the design and retrofit cost compared to switching to distillates, the time required for ship to be taken out of service for the retrofit operations, the elongation which may reduce the range of port to call, the bunkering challenges and the bunkering procedures that have to be determined, statutory challenges, the LNG fuel cost pricing challenges, and the LNG infrastructure challenges, while moreover, more tank space required to accommodate enough LNG to cover all the itineraries, the onshore bunkering logistics that are still under development, the rules and the regulatory framework that is currently being under development and its outcome is still debatable, while also the more sophisticated fuel equipment required, and finally the public perception, which is currently not fully known with regard to the fuel, LNG as fuel for vessels. But now where is the point where we're going to display the future outlook development of the LNG. The world bunker market will certainly be split between different fuel solutions. LNG among them appears to be the more sustainable solution in many cases. Certainly, the economics are not always in favor of LNG, depending on the forecasted prices, but all aspects have to be addressed. The development of LNG as bunker fuel will necessarily be progressive and slow. We distinguish three phases of development. In the first phase of development, short-sea ships in ECA with fixed routes will develop a high proportion of new-built ferries and ro-ros and a small share of new-built or existing product tankers. The ships will be impacted by the regulations in 2015, and competition between ship owners will be strong. Because of design and stability issues, many of these vessels will not be able to install scrubbers. Many inland ships will run on LNG as well, which should increase the LNG quantities available in port in order to reach a certain scale. The expected volumes in 2020 represent between 3 to 5 MTPA of LNG in the North Sea and the Baltic Sea, and the same volume in North America. Mediterranean ships could represent an additional 2 to 3 MTPA by 2024. In the second phase, some deep sea liners will run on LNG. This will be mostly new builds since retrofitting appears very challenging to perform. Major container ship operators will first test the solution by ordering a few ships to run on LNG, but in view of the consumption, this could add up to significant volumes. If the tests prove positive on operational and economic aspects, container ship owners will most likely decide to diversify their fuel and technological risk by switching part of their fleet to LNG. By 2020, deep-sea container ships are expected to represent only 2 MTPA of LNG consumption, but this will grow respectively to 5 MTPA in 2020 and 15 MTPA by 2036. A third phase of development will start around 2025 once LNG is available in several ports in North America, Europe and Asia. Short-sea ships without fixed routes but sailing in regions where LNG is available may then convert. Some deep-sea VLCCs or bulk carriers could run on LNG as well, but the need for flexibility in the routes could reduce their possibility. It is naturally difficult to predict the volumes at stake that might switch to LNG in this phase, but it's unlikely that LNG will be a common fuel for these ships. Conservative estimation would be around 5 to 10 MTPA by 2030. This brings us to the end of our presentation, where the concluding remarks are illustrated. The introduction of any alternative energy source will take place at a very slow pace initially as technologies mature and the necessary infrastructure becomes available. LNG presents the first and most likely alternative fuel to be seen as a genuine replacement for heavy fuel oils for ships built after 2020. The adoption of LNG will be driven by fuel price developments, technology, increased availability of gas, and the development of the appropriate infrastructure. Pricing, although, does not seem to be a major issue. Most ship owners are interested in securing the extra investments needed for LNG propulsion. So, discounted prices in relation to gas oil or oil-indexed contracts for a given duration will ensure that ship owners meet their payback time expectation. Except for the odd unknowns, and substantial part of the LNG economic advantages could be then defined contractually. Oil index pricing for LNG is the industry standard for current contracts, so it seems that suppliers and ship owners' expectations could easily converge. Moreover, there are a number of considerations and hazards associated with LNG as a fuel, from ship design and life cycle through to bunker operation and crew training. The rules appear to be based on each component within the system rather than the entire gas supply chain operation. Therefore, several gaps exist which owners and operators should be aware of. Employing well-educated and trained professionals is essential to promote the safe, efficient, and environmentally friendly use of supply of LNG as marine fuel. At present, there is a significant shortage in the availability of suitably qualified personnel and no established regulatory framework. There are also few educational institutions with the necessary resources to provide the training. Further on, a clear, stable regulatory framework is essential to develop the market. It should address each part of the value chain, from the truck and the ship transportation, storage and bunker facilities, ships using gas as fuel, and transfers between them all. So far, many uncertainties subsist concerning regulations, which are clearly a barrier to development. Investments in building the supply chain have therefore an implicit regulatory risk that has to be reduced. A number of countries have found a good way to approach this issue. It involves cross-functional working groups with representatives from the industry and administration as an essential factor to allow regulations to develop relatively fast. It is in everybody's interest for the different stakeholders to work together in order to move forward, ensure a stable regulatory framework, and a safe supply chain to foster realistic and economically feasible development investments. Finally, many costly investments must be made to launch the market. The investment capacities of many stakeholders along the supply chain might not be sufficient. Therefore, funding programs, subsidies, and/or tax benefits are needed to support the industry to create what is necessary for ship owners to comply with regulations. And at this point, we end our presentation. Thank you very much for your attention. The next presentation will be in around will start in half an hour. Thank you very much. Δεν το κλείσει αυτό.